So our lecture had some sound issues, so I'm going to do a really quick lecture on the notes. I apologize for potentially not having some of the demos intertwined in here. I'll try to splice them in, but I'm not sure if that's going to work. So today we are talking about reaction mechanisms and activation energy. All right, so a reaction mechanism, as you can read on the screen, is a series of steps in a chemical reaction. This is the thing. A reaction may look simple. Like it may look like it's just reactants making some products, but there's always more than meets the eye, and an equation doesn't show all the details on what is exactly always taking place. So I have an example here. Nitrogen dioxide reacts with carbon monoxide and produces nitrogen monoxide and carbon dioxide. Great. Here's the thing, and it's not your responsibility necessarily to know all the steps, but if I give you them, you're going to figure out how to utilize them. This equation actually uses two different steps. Sorry for being offset. And these two equations, you'll notice if you add them all up, they'll make the overall equation. Well, here are two really important elements that are involved in this. The NO2 cancels out once, and so does the NO3. By doing that, I can add up those two reactions to create the overall reaction. Well, there are some important vocabulary words that go along with this. The yellow compounds up above, those are called a catalyst. And a catalyst speeds up a reaction. What is important for you to understand is how to identify the yellow versus the blue is that the catalyst was introduced. It did not enter the equation as a byproduct or as a product in one of the reactions. It was a reactant in the beginning. And the order of the steps matter. If I would flip the first step and the second step, then that changes everything. But the yellow ones are a catalyst because it is introduced in the reaction. Notice though, it cancels out. An intermediate is formed and then consumed. So it was created in the reaction. But it does not make it in the final reaction, the overall equation. So I did a demo, you saw it during Chemistween, of decomposition of hydrogen peroxide. Here's the equation. Hydrogen peroxide breaks down to make H2O and O2. If you did balance that out, there should be a 2 in front of the H2O2 and the H2O for the coefficients. But if we poured out some hydrogen peroxide, it's just a colorless liquid, and have it sit in a beaker, it would be an extremely slow and extremely boring reaction. You would not see really anything happening as it's slowly turning into water and oxygen. But you can add a catalyst. So what I had everybody doing, and if you'd like to pause it for a second, try to figure out the catalyst and the intermediate in this reaction if you'd like. It is important to note that you don't necessarily need to have a catalyst or you need to have an intermediate. They both don't always exist. One may exist and the other one may not. But in this case, there is one of each. The I is the catalyst and the IO minus is the intermediate. So what I did in what's called elephant toothpaste is that you add some potassium iodide. So you're adding iodine into the hydrogen peroxide, and you add a little soap to help capture the oxygen gas, and boom, you get elephant toothpaste, which is a big, huge foaming reaction. All right, the other thing we are talking about today is activation energy. So I have two energy curves up, and think about if you're riding a bike for a second. So you're sitting on a bike where the letter R is, and you got to pedal really hard to get up the hill, right? You got to put a lot of energy. You got to put a lot of energy up in the hill. But if you get over that hill, it's smooth sailing. You get to easily ride down the bottom of the hill, and it's going to happen. There isn't much you can do about it. It's the same kind of idea with activation energy in chemical reactions. Certain reactions require more energy than others to get going. And if you can achieve that activation energy, then that reaction will start, and it's really difficult for it to stop. Here's an example. Paper. If paper is just sitting out, it slowly reacts with oxygen. And a good example of that and proof of that is that if you look at really old newspapers, that they have turned kind of a yellowish or an orange, right? But that is a really slow process. It's happening over many, 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 many years and a lot of interactions with oxygen. But if you take a piece of paper and you light it on fire, it is not reacting with the fire. Fire is putting in enough energy to allow the paper to react with the oxygen in the atmosphere. And boom, you've hit the activation energy and you're able to proceed with the reaction. So it is important to understand how you measure and where you measure the activation energy. So first, I'm getting ahead of myself. These two reactions are very different. The first one is an exothermic reaction because the reactants are higher than the products on an energy scale. So you've lost more energy than you started with. And the second one, the endothermic, where the reactants are versus where the products end. The products end on a higher energy than where they started, so that means you have gained energy. But how do you measure activation energy? It's from where you start to the peak of that energy curve. That's how much energy is required. So that is the activation energy and how you'd measure it for each situation. There's one more key element that you could measure off of this. So then the difference between the reactants and the products are what we would be calling, and I'll talk about the other thing in a second, is enthalpy then. So notice that the enthalpy on the left, the exo, that's between the reactants and the products, but I am losing energy, and the reactants to the products, it's very small, but I'm gaining energy in that one. But sorry, I got ahead of myself. The activation energy, you could write this down. It's the threshold energy that must be overcome for the reaction to occur. All right, but you could also kind of combine the two. So here is an energy curve, and I've already labeled it as an uncatalyzed pathway. All right, so that's the pathway that the reaction is going to take from the reactants to the products. But what did we just do previously? We added a catalyst. And what does a catalyst do? Catalyst speeds up the reaction. So think about you being on the bike again. And if you were on your bike and you started from the reactants and you ended your products, if you wanted to get there faster, what would you do? You got to take a shorter hill, or you have to take a shorter path. So hopefully this makes some sense, that this would be a catalyzed pathway. And that is actually how and why a catalyst works. A catalyst is lowering the activation energy, which causes the reaction to happen more quickly. So you should be responsible and understand the difference between those two drawings. Lastly, sometimes we are going to be calculating activation energy. This is not an equation that you have to have memorized. So note it's a natural log of two different rate constants equaling the activation energy over our gas constant times two different temperatures that are subtracted from each other. Two things to discuss. One, there are two temperatures and two rate constants. As we change temperature, that's why we have a different rate constant. If you're at a constant temp, it's always the same rate constant. But if you increase or decrease temperature, the molecules are going to be moving faster or slower, causing more or less interaction, which causes a huge effect on rate. Okay. Secondly, you may see the equation with the K1 and the K2 flipped. If that's the case, simply you will also notice that the T1 and the T2 will be switched. So if it's K1 over K2 on the left, then it would be 1 over T2 minus 1 over T1. That would be the only difference. Be sure to use the proper R value. I have it written there. Why do I know I have to use that one? Because it has joules in it, and above that is activation energy, which energy is always dealing with joules. Lastly, we discussed or ended talking about marble statues and acid rain. I will try to splice that part in because I know I did have sound, but I'm not quite sure I will be able to. So hopefully we will. You are responsible for determining the rate of reaction and the orders of reaction between hydrochloric acid and calcium carbonate, which is a major component of marble statues.